As you are progressing, there is more and more you can do. And ultimately, you can write more code. You will also often work with other developers, sharing your code and collaborating on implementation. At this point, it's vital to ensure that you're writing a clear, well-structured code, or, to use a popular term in software engineering, clean code. So, what is clean code? Clean code is code that is easy to understand and easy to change. Like a good book, clean code communicates the story of what you want the computer to do. Why does it matter? Your code needs to work as intended and solve problems efficiently. To do this, your code must be easily testable, modifiable, and expandable by other humans, or, in other words, your teammates. Beyond creating an enjoyable environment for us developers to work in, it enables us to implement efficient and elegant solutions in short periods of time. Always remember, if you write messy code, the next person who has to deal with it might be you. So, how to achieve that clean code state? There are two components to it: the writing style and the code architecture. The writing style we've already covered in previous courses. I'm sure you're already master of that. Code architecture is about how we design logical components. Object-oriented languages offer powerful techniques. However, without a proper system, the code can become messy and unsustainable. To keep our logical components, objects in particular, in check, follow 5 principles called solid principles. The first one is the single responsibility principle. A class should be responsible for as little as possible, ideally single task with a number of subtasks. Think of it as an assembly line. Each part of the line does one operation. Second principle is the open-close principle. This means that the code component should be open for extension and closed for modification. Let's take a bicycle as an example. Various attachments can be purchased to modify or add functionality, but the original bike will remain unchanged. The third principle is the least cost substitution principle. It addresses the potential dangers of using inheritance and suggests avoiding dramatic modifications in subclasses that break parent functionality. To go back to our bicycle example, if you get on a bike with an attachment, you still should be able to pedal and steer like you would on the original version of the bicycle. The fourth principle is the interface segregation principle, which says don't impose unnecessary requirements. For example, if you wanted to take your cat for a ride, you'd need a small cat carrier attached to your bike. How frustrating would it be if all cat carriers came with parachute attachment that you would also have to mount on your bike? And the final one, the dependency inversion principle. This one suggests making code components the least dependent possible, using abstraction and dependency injection. Continuing with the bicycle example, it doesn't need to know which particular attachment will be connected to it, as long as it has matching attaching mechanism. An attachment, in its turn, need not know which bike or even a different vehicle it would be attached to, as long as it has a matching attaching mechanism. In the next chapters of this course, we'll be paying attention to many code design decisions and ensure optimal implementation.